In this video, I want to review analog to digital conversion under a caveat circumstance, specifically when we receive signals that are outside of our discrete range of finite values. So for this, I'm going to go to the board. Now let's say we have a waveform. Think of a sound waveform as visualized on a computer or in your favorite audio player. So we might have a waveform that looks like this, somewhat extreme. And by itself, it looks fine. But in the analog world, whatever happens, happens. When we try to bring this into the digital world, we may find that our analog to digital converter doesn't address the complete spectrum of the wave we might encounter. And this happens sometimes. So let's draw that range as two horizontal bars. So let's say this is the peak value that we can convert, and that this bar at the bottom represents the low value we can convert. Now, the analog to digital converter has to do, another color pen here, has to do something with these individual segments here. So here's a piece that is outside of its representational range. Here's another piece, another one, and still another. So we need to do something with those. And most commonly what's done is we don't just discard them. That would make an unusual waveform, because then the resulting waveform would get up to here and then suddenly be, well, we'll just pretend silent for a moment, and then pick up again, and that might have a stuttering kind of effect. Instead, when we get too low and go beyond our lowest realm, we do what is known as clipping, and we reinterpret this waveform as if it was consistently the lowest value. We don't change the shape of the waveform before it, and we don't change the shape of the waveform after it. We just clip it, sort of like truncating in integer division. So the same thing would happen here. We would clip this at the low end. Clipping is for the low end. At the high end, our values would saturate. Remember that behind the scenes, the values we will store are a series of bits that contain zeros and ones. And traditionally, the all zero values are easy to think of as low values, as the lowest. But at some point, the representation we have will reach our maximum possible value, and that might be all ones. And when we receive the signals that are outside that range, the analog to digital converter will saturate or send back saturated values, values that are saturated with ones. So it's basically the same thing as clipping. It's just that saturation happens on the high end. Now, this doesn't only happen in the analog to digital conversion process where we're taking a signal from the outside world inside the computer, right? Sometimes inside the computer we actually have scenarios where this same kind of action might need to take place. So in digital signal processing computers, very often once we have data in the computer, we may be doing mathematics for a particular algorithm, specifically the type of things we might where we might be generating data that's going to be output in the form of, say, audio also. And we don't have the ability to produce waves or produce signals that go beyond our digital to analog representational range, right? And so we might have to do the same kind of clipping or saturation. And so we might have numbers that are high. You know, we might have a large number, and we might multiply it by another large number. And instead of letting those numbers overflow and wrap back around like an odometer in a car, which the mathematics inside a computer traditionally does, in certain processors we can set a clipping or saturation mode to be enabled. And when we do the arithmetic, if we get a value that is too high for our representational range, it will saturate, no matter how much higher it should have been. And if we do a piece of mathematics that results in an answer that is lower than the bottom of our representational range, we won't wrap back around. Instead, we will clip at, say, all zeros, or whatever the equivalent of the lowest represented bit pattern is. If we didn't do that, and we let those calculations torally wrap around, like when an odometer has all nines and that lowest order 9 finally rolls over to a 0 and the zeros cascade all the way up, and the whole odometer says 0. If we didn't do that, then back here, these waveforms we were seeing before, I'll use green for this, where this waveform went up, it might suddenly have wrapped around to the bottom like this. And where this one went down, if it would have wrapped around to the top, then we would have had this amazingly unusual waveform. Whoa. Something like that. Now, for certain basic arithmetic, that kind of thing, that overflow is okay. But for a lot of signal generation, where we're doing sort of the opposite of analog to digital conversion, this kind of thing would be unacceptable. And so we have to make sure that our calculations also clip and saturate.